Okay, so in this section we'll talk about tangent normal and binormal vectors. And let me just define them first, and then maybe we'll talk a little bit about what they are. So we've already seen this. So this is all under the assumption that we have some vector r, vector valued function r. What was t of, so capital T of t, this is the unit tangent vector, so how is that defined? Okay, good. So, yeah, so it's the, yeah, we want the direction of the tangent line, right? But we want to scale it down to be of length 1. So it's r prime over the magnitude of r prime. Does that make sense? And if we're thinking about motion, I'll just mention, right, it's velocity over magnitude of velocity then, right? Okay. So no. So by definition, what's the magnitude of t? Capital T. It's the unit tangent vector. So what's the length of the unit vector? Whatever vector it was, we divide by its length. So what's the new length? Shrunk always to be, starts with 1. 1, is that okay? So you get a vector of length 1 all the time. And so we did an example, we proved this result that was, if you had a vector valued function where the magnitude was always constant, that it was perpendicular to its derivative. So if you don't remember that, it's not a big deal. But the point is, this guy, or this fact, implies that t of t dotted with t prime of t is 0. Okay? And so t prime and t are orthogonal, or perpendicular. So your derivative of your unit tangent vector is always going to be perpendicular to your unit tangent vector. And so we define, the unit normal to be this vector n of t, which is just the derivative of your unit tangent vector over that magnitude. Okay, so the derivative of the unit tangent is going to be perpendicular to the unit tangent, but it might not be of length 1, and so we do the same thing. We take it and we scale it back to be of length 1. So remember before when we were talking about motion, we said, right, your velocity and your acceleration, you got a curve, goes like this. Your velocity vector is going to point off like that. Your acceleration will point somewhere in the middle, not necessarily perpendicular, but if we shrink this down to a unit vector and take the derivative of that, then it will stick sort of straight into where you're curving, if that makes sense. And so that's what we're going to be after. I'll draw that picture again in a second. So that's the unit normal, and then the binormal vector. I'll just write it this way, b of t. And so we're just going to do the cross product of those two vectors. So t cross n. And maybe just as an aside, the magnitude of b is the magnitude of the cross product. And if you remember, the magnitude of the cross product was the magnitude of t, the magnitude of n times sine of the angle between them. And so if they're at right angles, what's the angle between them? 90, so pi over 2. And so what's sine of pi over 2? 1, and so what's the size of b? 1 times 1 times 1, right? And so the magnitude of b is also always 1. Okay, so all three of these vectors are going to have length 1. The first two are a pain because you got to make them of length 1, and then if you created b or t and n correctly, then b is automatically the right size. Is that okay? All right. All right. Let's just do one example here. Find the equation of the line tangent to cosine of t at t equals pi over 3, and find the unit tangent vector. So this really isn't a new problem. This could have been in a previous section. Oh, I guess I completely forgot to draw my picture that I wanted to draw. I'm going to squeeze my picture right here. So, okay, again, without getting too bogged down with the ideas, you have some curve. Let's assume we're moving like this, okay? And so we get to some point. If I'm at this point, where's the unit tangent vector going to be pointing? It'll be pointing, right, we're curving this way, so it'll be a vector of length 1 in the direction of the derivative, right? So you get there. And then, so this is where t will look like that. B, this is, again, I didn't draw this perfectly. Sorry, n is going to be perpendicular. It's going to point into your curve. It's hard to see in 3D, but your curve comes like this. Your unit tangent will be this way, and then your n will point inside of your curve there. And then where's B in this picture? So it's t cross n. So it's t cross n, right? Cross product, right hand rule. So B is just going to stick up like this. That make sense? And so the way you should think of it is if you are traveling through space and you're curving like this, right? This is forward. Think of that as like your x, your y, and then your z direction. Does that make sense? But the point is your frame of reference might change as you move along a different curve. And so the idea of these guys is to keep a fixed sort of frame of reference, somewhat fixed, right? It changes, but it's fixed relative to you moving through space. That make sense? So we don't do a ton with this. If you took a differential geometry class, you do all kinds of stuff with these vectors. But we just want this basic idea. And so come back to this one. Take your derivative, find a tangent line using the derivative, right? And then once you have the tangent line, you'll already have that derivative, so just compute your unit tangent. If you want to try computing capital N, go for it, and we'll see how painful that is. So I'll give you a couple minutes to try this. Okay, so let's go through this. So you need to calculate your derivative. That, right? You want, so let's just do the tangent line sort of as its own question. So in order to find the equation of the tangent line, we need the point we were at, right? So we need the original r of t, and then we need the direction, so that's given by the derivative. So we're gonna need r of t, and then r of pi over 3, and then r prime of pi over 3. So what's r of pi over 3? So pi over 3 squared, right? Pi squared over 9. What's sine of pi over 3? Root 3 over 2. Here's pi over 6. Here's pi over 3. You 1, 2, root 3. Sine is root 3 over 2, right? And so times 2. Oh, sorry. Times 2. We'll just get root 3. And then cosine is 1/2, right? So times. It should just be. Oh, back still up in the original, right? R of. And then r prime. So that one will give us 2 pi over 3, and then these flip, right? So this one's 1/2, well, 2 times 1/2, right? So 1, and then this one's now negative root 3. Does that make sense? Okay. So with that in mind then, what's your tangent line? I'll call it L. So if we do a vector valued function here, equation of line, it's the point plus the direction times t, right? So what does that give us for the x values? So we get pi squared over 9, right? That's your point position plus 2 pi over 3t, comma, root 3 plus t, and then 1 minus square root of 3t. Does that make sense? Just point plus, or just to be clear, your initial point, right, plus t times your direction. Okay, so good. That's that. What about the unit tangent vector then? So capital T is just r prime over the magnitude of r prime, right? So what's the magnitude of r prime? That's just a function of t. It's the square root of 2t squared, right? Plus 2 cosine squared plus 2 sine or minus. Yeah, so it'll be 4t squared plus 4, right, when you do that? And so maybe I'll just jump to that. So you're going to end up with 2t over the square root of 4t squared plus 4, right? And then 2 cosine of t over that same thing. This is, looks a little sloppy here, but I'm going to do it anyway. Slide across the board here, and then find negative 2 sine of t over that same 4 t squared plus 4. Now we could definitely pull out the 4's, right, and make square root of 4 as 2. And so it'd be, well, it'd be t over the square root of t squared plus 1, right, cosine over the square root of t squared plus 1, and negative sine over that. I'm not going to bother with that, but now, if we want to compute n, what do we have to do? We have to take the derivative of this, right? N was the derivative of t, and then divide by the magnitude of that resulting derivative. And so my only point here is that can get really ugly pretty quickly, right? So there's nothing clever that you're doing. It's just ordinary derivatives, but it'll get really ugly looking. And so I decided not to bother with this one because it's going to get too ugly, but in theory, we should be able to calculate all of those. So let's calculate T, N, and B with the easier one. So find T, N, and B for, we'll make it almost the same, but we'll get rid of that quadratic. We'll just make it 3T, and then we'll just do 3 sine of T, 3 cosine. Okay. So try to calculate the T like we just did. Once you have that, it gets derivative, and then you should be able to calculate N and calculate the B from there. It should be pretty quick. I'll give it a couple minutes to try that.
Do we have to same T?
No, so generic, like we did here, right, with an arbitrary T. So no, don't do it at a fixed value. So you can't find, right, you can't find N or B for a fixed value because you need to find the generic T in order to, or capital T to take its derivative. So I'm going to just start working through these. Plugging away if you feel like you know what's going on. So you end up with that for your r prime, hopefully, and then your derivative, or your magnitude is this, and what's that simplify down to?
3 times roots of 2.
Okay, good. So square root of 18, right? You get a 9 and then another 9 from the 9 cosine. And if you want to simplify it to 3 root 2, that's fine. If you want to leave it like that, that's fine as well. And so your capital T is what? Let's move over here. So capital T is just that divided by your square root there, right? So capital T is 3 over 18. Root 18. 3 cosine. Root 18 and minus 3 sine. 18, good. All right, so now how do we calculate n?
Oh, yeah.
first take the derivative of that, and again, just remember that's not n, but it will give us n. So what's our derivative?
0, negative sine t,
Yeah, good, and then,
negative cosine t.
yeah. Okay. Now, you might have figured this out already. When you see things like constant times sine, constant times cosine, you know sine squared plus cosine squared is 1. And so the thing of length 1 is just to divide by that constant. But let's go through it anyway. So the magnitude of this guy, this t prime, right, is the square root of what?
9 over
9/18 sine squared,
plus
9/18 cosine squared. Right, and so you just get square root of 9/18, which is 3 over the square root of 18, right? And so now when you divide through to get your, and you're just going to clear off those constants in front of them. And so your n, which is t prime over the magnitude of t prime, just becomes 0, negative sine, negative cosine. Is that okay? And then finally, b is just the cross product of those guys, and so b is just t cross n. And so let's just write these out. So t was 3 over root 18, right? 3 cosine of t over root 18 minus 3 sine over root 18, and then n is 0, negative sine, negative cosine. And so what do we get here?
negative cosine squares over
Okay,
root of 2.
so negative 3 cosine squared over root 18, and then minus, and then they'll cancel, right? So 3 sine squared over root 18. Is that okay? And so you can save some time if you get confident in that, but let's just work our way through these slowly. How about the middle one then?
3 cosine t over square root of
Very good.
18.
So it's 3 over root 18 times negative cosine, but then we negate it, right? So we should get that. And then finally,
Negative 3 over
3 over root 18 sine, right? And so this first one cleans up to be just negative 3 over the square root of 18. Okay? And again, you can clean that up. It's really 1 over square root of 2, right? But I'll just leave them like that. Okay. So there's B, there's N, and there was. That make sense? And again, no matter how ugly these things are, at least in theory, we should be able to calculate. But in practice, they can get pretty messy. So be able to compute them. Again, keep in mind what they're representing, right? They're representing as you move along the curve, it's sort of this changing. Think of your axes like this, and those sort of rotate as you move through space. And it's kind of keeping you oriented with the way you're moving. So the one vector is always pointing in the direction that you're moving, and the other vector points sort of inside to where you're curved, and so on. Okay, so I don't know why that projector's looking funny. I didn't want to have to draw these pictures, so I'm just going to pull the book's pictures up from here. So here's a point in space. Even with the book, it's a little bit hard to see. So you get 3 vectors that show up, right? And so it gives rise to really, well, I suppose you could say 3 different planes, but there's 2 important planes. And so the first one is the plane that's defined by your normal vector and your vector b, and So that vector, or that plane is perpendicular to t, right? And so if you think of a curve moving through space, this is just the plane where it sort of moves through perpendicular to that plane. Does that make sense? So this is called the normal plane. Okay, so you calculate it by using t as your normal vector. Does that make sense? It should be normal to that. And then the other plane is the one that goes, that n and t sort of sit in. And so you should think of that almost as, right, your curve is moving through space, and that's kind of the plane you're in at that moment, right? You're curving through that plane. And so this is called the osculating plane. I don't know if they wrote that. Osculating plane. Don't get too bogged down by the terminology. Just realize you got a normal plane, and then you have this other plane, the osculating plane, and it represents, like I said, the plane you're sort of moving through at that moment. Okay? And so that one's found by using b as your normal vector instead. That make sense? So let's just stick with this example we had here. So find the normal and osculating planes for the R of t in the previous example. Well, let me just write it out. What was it again? 3t sine of t cosine of t at this point 3 pi 0 negative 1. And so we have the vectors we need on the board over here. We're just going to make use of them. So your equations here are equations of planes, right? So we got to remember back to what the equation of a plane looks like. And then you're just either using t as your normal vector for the normal plane, and then b as your normal vector for the osculating plane. That make sense? So if we got that point, 3 pi 0 negative 1, let me just do this. What t does that correspond to?
So equals to pi?
Equals pi? Right, so if all you have to do is look at this, right? 3 pi, 3t, so if 3t equals 3 pi, then t has to be pi. And then let's just confirm when we plug it in, sine of pi is 0, right? Cosine of pi is negative 1, so we got the right point. Does that make sense? So that's your first step, is to find out what the t is. And then we'll just calculate these things. So let's just do them in order here. We'll do the normal plane first. Okay, and so again, if you look back at the picture, right, the normal plane is just using the unit tangent as its normal vector. So we're going to need t of pi. So t was over there still. And if we just plug in pi, we'll get 3 over the square root of 18, right? And then pi goes into cosine and sine. Sine, or cosine of pi is minus 1, and sine is 0, and so we should get negative 3 over root 18, 0. Is that okay? And so now we want to use this point, right, with this normal vector. And so what's the equation of a plane? It's vector times x minus x component, right? So it'll be 3 over root 18 times x minus 3 pi plus, well, it'll be minus, right? 3 over the square root of 18 times
Y
minus 0, so just y, and then plus 0 times z minus negative 1, right, if that had to be in there. We'll just end it like that. So you get that for your first plane. And then the second plane, osculating plane, we'll do the exact same thing, but we use b as our normal vector, right? And so there's b. So we need we just need b of, what do we say was pi? And so now b is right there, so it's negative 3 over the square root of 18. Cosine is negative 1, sine is 0, and so you get negative 3 root 18, 0. And so then look at this plane. So again, this is your normal vector, same point, right? So it's negative 3 over root 18 times x minus 3pi, and then plus another minus 3 over root 18 y. Does that make sense? All right. So I think that's all I need to computer. I'll turn lights on, shield your eyes. All right, last thing then from this section. Decide how much I want to do with this. Well, let's do this. So we mentioned before that if you have this curve running through space, you get your unit tangent vector looks like this, right? Your unit, or your normal vector, unit normal vector will look like this. Okay, and acceleration is going to be in between those guys. So the acceleration will look something, let's just draw like this. Okay, again, the tangent, the unit normal, they don't really care about how you're moving through, how fast you're moving through. They're going to be just functions of the shape of that curve, right? Whereas the acceleration, that depends on how you're moving through the curve, and so it depends on the parameterization that you end up with. Does that make sense? And so what we want to talk about is, well, if these guys sit here, you should be able to write, right, the vector A as how much, I don't remember what our notation, oh, a sub t. So, how much acceleration is in the tangent direction? Does that make sense? So that would be the length of this curve if you move this down here, plus how much of the acceleration is in the normal direction times the normal vector. And then that should be a way to rewrite your acceleration. Does that make sense? And so you talk about the tangential component of acceleration is the a sub t, and the normal component of acceleration is that a sub a. Does that make sense? And I don't know. I think I'm not going to bother coming up with the formulas. They're not difficult to come up with, but I'm just going to give it to you. So a sub t should just be acceleration dotted with your tangent, and if you just look at what that turns out to be with your tangent, it's the dot product of your first and second derivatives over the magnitude of your first derivative. Okay? Hopefully I wrote these down right. Okay. So the amount of it in the direction of n, that's just your dot product with n, and that turns out to be the magnitude of the cross product divided by, of the cross product of the first and second derivative divided by that. Okay? All right, so let's just use these formulas for right now, and let's do an example here.
Just as a heads up, there's 3 minutes of video left on this.
There's 3 minutes.
Yeah, so,
All right, let's try to crank through this one real quick.
I mean, I can delete some things, but I don't know if you've uploaded everything.
Oh. Actually, let me just change this up. Okay, so let's do these at t equals 5 or 2. Okay, so all we have to do is calculate these things in first and second derivative and punch them. So first derivative, -2 sine of 2t, right? I plus 2 cosine of 2tj, second derivative, -4 cosine of 2ti minus 4 sine of 2tj. And when we're computing these things, we really only need them at these values, and so I'm just going to go ahead and find them at these values. So r prime of pi over 2, r double prime of pi over 2, when I plug these in, what am I really plugging, or what am I getting out for the sine and cosine? I'm getting sine of pi over, just pi, right? Shoot, I want to do, let's do this instead. Let's do pi over 8. Got a more interesting answer. Pi over 8. So now when I plug that in, where am I evaluating at pi over 4, right? So what do I get? Root 2 over 2 for each of these, right? So what do we have? Negative root 2, root 2, and then negative 2, root 2, negative 2, root 2. You just have to evaluate these things. So A, T, I put arrows over these, I don't need those, those are just numbers, right? So AT is just, right, R prime dotted with this. And so when you dot these together, you get negative and negative, you'll get 2, root 2, so you'll get 2 times 2, and then minus 2 times 2, right? All over the size of R prime. I won't even bother with that because that's 0, right? So this is telling you that you have no acceleration in that direction. I'm surprised by that. You should go back and double check if we screwed this up. So it depends where you're at. And then A sub n should be the magnitude of the cross product. Oh shoot, here's why. Wow, that's okay. So, when you do this cross product, you need to throw things into 3 dimension, but that's going to be, oh, I don't like what happened.